Okay, so the purpose of this video is going to be proving these two very fundamental large theorems of calculus. Most calculus textbooks state these as a fact and say, hey, proof exists out there, but we're not going to spend time proving them because they're difficult. They pretty much put you to some other book that actually has a proof available. And that always kind of bugged me because to me that means there's like a huge hole in the logic of the development of calculus. So my goal in this video is to as efficiently as possible provide proofs to both of these theorems. It will feel like heavy mathematics. What we are doing is, in this video, we will be doing a level up of mathematics, but it's going to kind of be like a bridge to calculus, the calculus we talk about, and the heavy real analysis. So bear with me. This might be a longer video, but this is going to be kind of like an experience of what a mathematician does. They go through proofs, rigorous proofs of results that are apparently so difficult to prove that the proofs are omitted from famous calculus textbooks. So that's what today is going to be. It's going to be kind of like patchwork on these famous calculus textbooks like Stewart's Calculus or Thomas' Calculus. They rarely, I don't think either of those provide proofs for these theorems. So this video will provide those proofs. So let's do it together. In order to do this, we have to say a property. Really, there's a property about the real numbers that make these two theorems accessible, these two proofs accessible, and that is the completeness of the real numbers. So let's start talking about that. So there's something that makes the real numbers different than the rational numbers. Both the rational numbers, so we have the rational numbers here, Q, which is the set of fractions, and the real numbers, both of these are fields, okay? So what that means is they have this specific set of axioms. They have the commutative property, associative property, distributive property for both multiplication and addition. They're both fields, and they're both ordered fields. So it kind of begs the question, if they're both fields and they're both ordered fields, what makes this set different than this set? And the difference comes into this idea of completeness. The real numbers are complete, whereas the rational numbers are not. There's a famous example. There's this set here of all squares that are less than 2. There is no upper limit in Q. In Q, there is no largest element. So in other words, if you grab me the set of all rational numbers whose square to Q has no largest element, or excuse me, the set of all rational numbers that square to 2 has no largest element in Q, whereas the real numbers do have a largest element. So in Q, there is no largest element, while in R, there is. So this Q has no largest element to this set, and this R does have a largest element. In fact, what we use here is we make that almost an axiom for R. We say that if we have a set in R that is bounded above, in other words, there's some real number that's bigger than the rest of the elements in this set, then there is some other bound, maybe our other bound, that is smallest or smaller than all other bounds. Okay, so let's talk about that literature a little bit better than what I just said. First of all, let's talk about what it means for a set of real numbers to be bounded above. It's an intuitive definition, but we have perhaps a subset of the real numbers. We know that a subset of the real numbers is bounded above if there is some set or some number in R that each element of our set is less than or equal to that number, okay? So a set of real numbers, A, is bounded above if there is some number that's bigger than all of the elements of A. That's what this says right here. So again, so bounded above, if there is some big number, it's not necessarily big, but there's just some real number out there such that A, each element of our set A is less than or equal to this number. Each element of A. Such a number B is called an upper bound. Okay, so that's what it means if a set is bounded above. And a little bit of a logical statement right here. If a number C is not an upper bound, what we have to do is do some nice logic and ask what does that mean. We have to ask what it means for a set to not have an upper bound, or what does it mean for a number to not be an upper bound of A. What that would mean is, well, if C is not an upper bound for the set A, that means there is some sort of element of A that is bigger than C, right? Because that would mean that, well, C is not an upper bound. After all, look, this element of A is bigger than C, which means it's certainly not the case that each element of A is less than or equal to C. Because look, there is some A that's bigger than C. That's the contrapositive, if you will. If a number is an upper bound, then each element of A is less than or equal to that number. If it's not an upper bound, you have to negate that, which means that there is some element of A. So this for each turns into an existential. We go from a universal quantifier to an existential quantifier. There is some element of A such that this is not the case, which would mean that A is bigger than B. So that's what it means for an element C to not be an upper bound. And that's going to be really important in our next definition. Okay, so here's where we started talking about how the real numbers are unique. In other words, or maybe not unique, but rather different than the rational numbers. What makes the real numbers different than the rational numbers? Like I said, you could flippantly say, oh, that is just the fact that the real numbers are complete. But what the heck does that mean? It has to do with this definition right here. A number B is a least upper bound of A. And honestly, you can hear that and just ask yourself, what would a good definition of a least upper bound be? And here's what we call what it means for it to be a least upper bound of A. Two qualities of a least upper bound. So this is a definition. A special number is a least upper bound of A if B, first of all, it's an upper bound of A. And if we have another number that's less than this upper bound, then we know something about that other number, that it's not an upper bound of A. In other words, there is no number that's less than B that's also an upper bound of B. This accomplishes the least idea. So if B is an upper bound of A, and any number less than B is definitely not an upper bound of A, because we want this number B to be least, then we can say that B is a least upper bound. Okay, another way to say this right here, I'll write this down. This is called the contrapositive. Another way to say this second condition, if we just take the contrapositive, so if P then Q, what you could say is if not Q, then not P, and let's say that. Another way to say 2, so notice this is 2 with a star. If Y is an upper bound, so if Y is an upper bound, notice what I did is I negated this statement. What I have to do next is say then the negation of this statement. If Y is an upper bound, then this special number B, the least upper bound, is definitely less than or equal to Y. Okay, so that's just simply a restatement, an equivalent statement of this second condition here, to be a least upper bound. Another way to say it, looks like I kind of give another kind of colloquial definition. A least upper bound is an upper bound smaller than all upper bounds, all other upper bounds. Okay? So that makes sense, right? That's what a least upper bound should mean. But this is just the mathematical language that we attach to it. So really important. If we have a least upper bound, then we know, first of all, that B is an upper bound, and that no other number less than this can qualify as an upper bound. That's what that says. And here we come to our big axiom. This is an axiom that differentiates the real numbers from the rational numbers. Big important axiom. Here we go. If A is a non-empty set of real numbers that is bounded above, okay, so I grab a bunch of real numbers, and I know that there is some sort of upper bound, then what I know is that that set has a least upper bound. This is not necessarily true in the rational numbers, but we are declaring this to be true about the real numbers. This is the defining axiom that makes the real numbers different than the rational numbers. If I grab a bounded set of real numbers bounded above, if I grab any bounded set of real numbers bounded above, then I know there has to be some real number that is both an upper bound and smaller than all other upper bounds. If I have any set of real numbers, non-empty set of real numbers that's bounded above, then there must be a least upper bound. Again, this is the axiom that says the real numbers are different and much more vast than the rational numbers. This is the axiom that quote-unquote completes the real numbers. Okay, so I am going to kind of, with this, hop straight into some useful results. With this axiom that we now have in our pocket about the real numbers, we can slowly build the tools to prove the extreme value theorem and the intermediate value theorem. This is going to be heavy. This is going to be a journey, but thank you for joining me. The first thing we are going to prove is that if we have a function that is continuous over a closed interval a to b, then that function must be bounded above on that closed interval. This is certainly intuitively true if we were to draw a picture. So what it means for a function to be continuous over a closed interval is that it has to have some sort of output at these two values. Okay, so it has to have some sort of output. I accidentally made it look like they were the same, certainly not necessarily the case. So I know my function has to cross those values, and I know my function's continuous. So once I start drawing my function here, I can't lift my pen. That's what that says. I can have these spikes, but I can't lift my pen. So what this theorem, super intuitive, says is, well, there's some number on this y-axis. If we were to extend this y-axis, big M, there's that number big M, for which all of my function values sits under that big M. That's what it means for a function to be bounded above. And we want to say that that's certainly true if our function is continuous and it's continuous over a closed interval. So let's look at this proof. I'll use this. I like this light blue color. I'll go with that. All right, so we have this axiom in our pocket. We will need to use that axiom. Proof. Let's suppose f is continuous, and I'm going to abbreviate it now. Oh, it looks like I already did in the theorem itself. That CTS is an abbreviation for continuous. Suppose f is continuous over the closed interval a to b. And our goal, of course, is to show that f must be bounded. And now that we have this tool that says something about non-empty bounded above sets, we want to grab a set that is non-empty and bounded above, but we want to grab a set that's non-empty and bounded above. That will help us in accomplishing this proof. So here's how I'm going to do that. I'm going to say let A be the set of x values in this closed interval such that f is bounded above on the closed interval a to x. Okay. I'm going to talk about this set right here. What I want to do, first of all, this is going to be really important. Our goal is to show that this set A is actually the entire interval. That way, we can say that if this set A equals simply the interval from A to B, then that means that by definition, F is bounded above on A to B. That's our goal. But first of all, we want to show that we can use this sort of new axiom, this completeness axiom, or this least upper bound property on this set. In order for us to use that, we need to make sure that this set A is not empty and that it is bounded above. Okay, so what I'm going to say is this. Notice A is non-empty because, well, A is an element of A. And to justify this, F is certainly bounded on the singleton set A to A. Again, that is an interval, quote unquote, that has only one element. So, I don't know, F of A plus 1 is a bound on that set. Also, A is clearly bounded above. Okay. And now that I'm saying this, I'm realizing that I actually need another tool that was proven in this week's theory video. So let me kind of go back and let's remind ourselves of this tool that we need. So check this out. There's another tool on the theory video that we proved. So I'm not just postponing the issue of making sure everything in a calc video or in a calc course is proven. This has been proven. If F is continuous at A, then there is some delta bigger than 0 such that F is bounded on A minus delta to A plus delta. Okay, so I know my function is continuous at this x value A. That means I can create a bubble around this x value. So I know my function exists here and is continuous here. I can create a bubble around my x value such that my function is bounded on that bubble. So say this is what my function actually looked like. I can always scoot away from A by a little bit. I can scoot away from A by a little bit if I know my function is continuous at A, and that won't cause my function to go so erratic that it's not bounded around A. There is some small distance that I can scoot away from A for which my function is bounded over that small distance. Okay, that was proven in the last video. It's not too hard to prove, but we will need that. That's actually really crucial because what I'm about to say is that A is clearly bounded above by B in particular. Okay, so A is definitely bounded above by B. After all, if you look at this definition of A, the values of A are forced to be in this interval, but B is some real number, and X cannot exceed B because X is an element. Sorry about that. The video glitched a little bit. As I was saying, I know that F or that A is bounded above, clearly bounded above by B in particular, because X is an element of this closed set. Okay, but what that means A has a least upper bound. Let's call it C. And that is where we're using that new axiom of the real numbers. The real numbers has each subset that is non-empty and bounded above has a least upper bound. That is the completeness axiom of the real numbers, and we just used it. Okay. Since C is least and an upper bound, and we also know that B is an upper bound, we know that C is less than or equal to B. Again, that's because we have two upper bounds, C and B, but C is by definition the least upper bound, so it must be less than or equal to B. We will show that C being less than B is impossible. So, let's suppose it were the case that C is less than B, and what we're going to do is reach something ridiculous. Okay, so C is less than B, so what I'm going to say is notice F is continuous at C. And therefore, well, you know what? Before I do this, I'm actually going to do something first. What I'm going to show is this upper bound, in this specific case with this set A, there's a very special property for A here. And let me make my highlighter a little bit bigger. Here we go. That's better. I'm going to show that if I am any element less than this upper bound, then I am a member of A. That's what I'm going to do first. So, and then we'll be able to show that C being less than B is impossible. So I'll even write that. But first, suppose, let's say L is some member or some element less than C. Since C is a least upper bound, what this means by definition is that L is not an upper bound. Okay, so first suppose L is less than C, then L can't be an upper bound, which means there must be a member of A that is bigger than L. In other words, or I can just say this. In other words, F is bounded on the closed interval A to K. That's what the defining property of being a member of A is this. F is bounded on the closed interval from A to K. That's what this says right here. If you are a member of this set, then F is bounded above on the closed interval, bounded above on A to K. But then F is also bounded above on A to L. Why? Because A to L is a subset of a proper subset of A to K. And if F is bounded above on the larger set, A to K, then it certainly is bounded above on a smaller set, A to L. But what this means is L is a member of A. Okay. So what we just showed, this is important, especially for later in the proof. If you are less than C, then you are a member of A. So C is the least upper bound of A. If you are any number less than C, then you are also a member of A. Okay, so this would be like A is leftward closed or something like this. Okay, but now we're going to go back on track. We will show that C is less than B is impossible. Let me also correct my proof here, or correct my word there. Notice F, so we're going to suppose, oh, here we go. So let's do this. Suppose C is less than B. And this is where we want to reach that contradiction. Then F is continuous at C. But by this lemma that we proved, or by this theorem that we proved in the previous theory video, then there must be some delta bigger than 0 such that F is bounded above on the open interval C minus delta 1 to C plus delta 1. Okay, let's just grab any x sub 1 in the left side of that interval. C minus delta 1 to C. Then F, well, then I can say this. Then x sub 1 is less than, is less than C, so that x sub 1 is a member of A. We just showed that. But if x sub 1 is a member of A, then F is bounded on the closed interval A to x sub 1. Okay, so that's what that means. That is the defining property of being a member of A. But also, I'm going to choose an x sub 2 at the left side of this bubble, so to speak, or excuse me, the right side of this bubble, so to speak. So that would be from C to C plus delta 1. Then F is bounded above, I should say that here, above, bounded above on the closed interval x sub 1 to x sub 2. Why? Because that is a proper subset of this open interval, and this open interval I know F is bounded above on. Okay? Thus, so F is bounded above on this interval, and it's also bounded above on this interval, so it must be bounded above on their union. Oh, but what does this mean about x sub 2? I think what that says is, look, I have that F is bounded above on the interval from A to x sub 2, which means that x sub 2 is a member of A. Oh, but that's a big problem. Because x sub 2 is bigger than C. And C was supposed to be an upper bound. And we've reached our contradiction. And therefore, C must equal B. Okay, so we suppose somewhere in here that C was less than B, immediately reached a contradiction, forcing C to be equal to B. All right. Now, you might be tempted to say we're done with this proof, but I think we're not quite done. What we have is that F is bounded over A to X for each X less than B. That's what we've shown so far. But we can extend this to X's including B by noticing that f is also continuous at b, technically left continuous. But what that means is there is some delta sub 2 bigger than 0 such that f is bounded above over, so we got b minus delta sub 2 all the way up to b closed, or including b. So we know f is bounded above on that interval, and then all we have to do, and remember, we also know that f is bounded above, I should say bounded above, I keep missing above, pedantic, but, so we know f is bounded above over the closed interval a to x for each x less than b, and that combined with this fact is going to allow us to land here. So choose, let's go x sub 3 in the open interval, b minus delta sub 2 to b open, so we're not including b there. Then x sub 3 is less than b. Therefore, f is bounded above on the closed interval a to x sub 3, but also the closed interval x sub 3 to b is a proper subset of the interval from b minus delta sub 2 to b. Thus, bounded above on that closed interval, x sub 3 to b. Okay, so let's see what we have. We have that f is bounded above on the closed interval from a to x sub 3, but it's also bounded above on the closed interval x sub 3 to b. Thus, f is bounded above on the closed interval a to b, and that's what we wanted to show. Okay, nice compact proof. There it is in one frame there. That is probably one of the bigger proofs of today's video. We're going to hop right into the next one, the extreme value theorem. Once we have this little proof here, the extreme value theorem is not so difficult to prove. So let's hop into it. The extreme value theorem, what does it say? It's not too easy to understand. That's also one of the reasons these calculus textbooks sort of omit these proofs, because they're very believable results, but your intuition often can lie to you. So let's say we have a function that's continuous over a closed interval, which means that when I start drawing this function, I have to connect to that other point at b somehow without lifting my pen, because I'm assuming it's continuous. Okay, so what does the extreme value theorem say? There is some point where this function is biggest. Okay, so it looks like this is that point. The extreme value theorem says that this x value, this special x value, exists such that f of d, f evaluated at that x value, that guy is bigger than f of x for all other x's. That's what the extreme value theorem says. Well, technically that's half of the extreme value theorem, but that's the half we are going to prove. It is very believable. A continuous function over a closed interval can't go haywire and shoot to infinity. Why? Because it always has to come back and connect to this other point, b. So that's what it says. It's pretty believable, but let's actually see the proof. We now know that continuous functions over closed intervals are bounded for sure. So let's see. Let's start our proof first of all. Suppose f is continuous over the closed interval a to b, then it's bounded too. But what that means bounded above, I should say. Thus, the image of F, if you don't know what an image is, that's okay. I'm going to tell you what this set is. This is simply the set of all possible outputs of F over that closed interval is also bounded. Since that image is clearly non-empty, just grab, F has to have an output at each of these values, so it's also non-empty. Here's where we use the completeness axiom, empty. It must have a least upper bound. Let's call it alpha, okay? So what that means, f of x is less than or equal to alpha for each x in this closed interval. That's what upper bound means. We also know it's lower than all other upper bounds, smaller than all other upper bounds. So, but this condenses what we want to show. We want to show there is some d in this closed interval, a to b, such that f of d, f evaluated at that d, is equal to this least upper bound alpha, okay? Because then I could replace this part with f of d, and that'll get us this part of the proof. I'm not going to prove this part. It's very, very similar. This video would be gargantuan if I proved both of these. But, okay, so let's see. We want to show that there's some d in here that such that f of d is equal to the supremum. Suppose, okay, so we're going to say suppose not, or suppose there isn't. So, in other words, what that means is instead of there is some d in the closed interval such that f of d is equal to alpha, if there isn't, then what that would mean is for each element of the closed interval, f of that element is not equal to alpha. So I'll say, in other words, suppose f of x does not equal alpha for each x in the closed interval. And here's how we're going to be clever together. With that fact, we are going to make a new continuous function. This function, g of x, must be continuous, abbreviate, over the closed interval, a to b. Why? Because the denominator is never 0. And we know that rational functions are continuous over their domains. That was stated in a previous video, in the theory video. That theory video was really in preparation for this video. I was very careful on saying the right things so that we'd have the right tools here. So we have that g of x is continuous over this closed interval because the denominator is never 0, because we are supposing that f of x does not equal alpha ever. Okay, so, but what do we know about continuous functions over closed interval? We know g is bounded. We just proved that. Bounded above. We're going to reach some sort of contradiction here. So let's suppose we have a some positive number. Check this out. Then what I'm going to create is a number that is definitely not an upper bound. I'm going to inch away from alpha, which I know is the least upper bound. I'm going to make it smaller. And then by definition of alpha, I know that this number here is not an upper bound, right? Because this is less than alpha. An upper bound of the image of f. But what does that mean? There is some, I'll call it x star, in A to B such that, so if this is not an upper bound, that means there has to be, of this image of f, that means there must be some element of the image of f that's bigger than this. F of x star here. Okay, well, let's just ask what that means. Well, that would mean that alpha minus f of x star is less than 1 over m, but by taking reciprocals, that implies that 1 over alpha minus f of x star is bigger than m, right? Oh, but shoot, that's a problem because that tells us that there is some element, or that g, what that tells us is that g is bigger than m. But that's a problem because m was arbitrary. I grabbed a random number, positive number, and showed that g was bigger than that positive number. What that means is g is bigger, or g gets to be bigger at some point than any number. So what does that mean? G is unbounded. But that's a direct contradiction to what we just proved. We know G must be bounded above. So G is bounded above, but it's also unbounded above. That's the contradiction. And therefore, this must not be true. So let me zoom out a little bit. So we have that G is bounded above and also unbounded, which means that this is false. In other words, this must be true. So I'll say this. Therefore, there is some d in the closed interval such that f evaluated at that d is equal to the alpha. In other words, f of x is less than or equal to f of d for each x in the closed interval. Oops. For each x in the closed interval. And that is the extreme value theorem. All right, I like that one. Slick little kind of constructive proof there. So let me zoom out. That is our proof of the extreme value theorem, and we have one more beast, you guys. Let's see if I can do this in 17 minutes. That would be impressive. Let's prove the intermediate value theorem. So we know what this one says. It says something like this. Say I have a function that is continuous over a closed interval. In other words, I know it has some sort of output at A, and I know it has some sort of output at B. Here, let me actually draw this a little bit higher because I'm going to need some room. Okay, so I'm going up here. Okay, so let's say I have a continuous function. I don't know why I did that. Continuous function, here's A, here's B. I know it has some sort of output at A, and I know it has some sort of output at B. And let's say I also have some sort of intermediate value, y star. I know my function is continuous, which means when I start drawing it like this, I can't lift my pen. But I have to get to that bubble up there. So at some point, I have to do something like this. What the intermediate value theorem literally says is this point exists. In other words, there is some C in between A and B such that f evaluated at that C is equal to that intermediate value. Okay, so again, that's pretty believable. Just understanding what a continuous function is, we understand the intermediate value theorem. It's not too hard to understand. But in order to prove this, I want to remind ourselves of a result we proved in the last video. Recall. If f is continuous at a is some random number, and f evaluated at a is less than 0, then there is some delta bigger than 0 such that f of t is also less than 0 whenever t is a member of this special set, and that's going to be the delta bubble around A. Similarly, if f of A were bigger than 0, then there is some delta bigger than 0 such that, this is proven in the last video. I'm not just telling you this is true, that's bad math. This is proven in the last video. Such that f of t is also bigger than 0 whenever t is a member of this set. So to understand what this says, it's not too hard to understand, but let's say I have some sort of function. Here, let's call this A, let's call this B. And here's my function. It looks something like this. And I know f of A is less than 0. And they could do something like this. I happen to know f of B is bigger than 0. And I happen to know that my function is continuous. Here's what that says. So here's my f of A, which is less than 0. Here's my f of B, bigger than 0. What this little result here says is I can create these delta neighborhoods, maybe this one. I can scoot out from A a little bit, and then all of my function values that are that far away from A, or excuse me, all of my function values evaluated at values in this delta bubble are also less than 0, okay? So if we have a continuous function that's less than 0, like we do here, then it's also less than 0 around A, or close to A. That's pretty much what it's saying. And of course, the opposite is the same. If f of b is bigger than 0, then I can create this delta bubble that forces my function to be positive around b. All right, so that's what that says. That's also pretty intuitively believable. And that's a fun little proof also. So refer to the theory video if you don't believe that one. It's a cute little proof. We have proven this already. And we have enough with that to prove the intermediate value theorem. Proof. Again, we are going to use the completeness of R. We have to. Suppose f is continuous over the closed interval a to b, and that I'll just say f of a is less than y, and y is less than f of b. So we have some sort of intermediate value. Okay. What I'm going to say is I'm going to make a new function. And that's going to be f of x minus this intermediate value. Okay. So what that does, what this function is going to do is shift this function, this f here, so this would be f of x. I'm going to create a g of x simply by taking this distance, y star, and shifting all of these values down by this distance. That's what this is. So here's my g maybe. So this distance should be the same as this distance. So just as long as you understand that. It should look something like this. Ugh, it's hard to do. So here's my g of x. All right, let me kind of clean this up a little bit, something like that. Again, this distance between these two should always be y star. That's the difference. So notice this, maybe you can see the motivation. G of x, or g of b, is bigger than 0, all right? And what that means is I can use this theorem right here, right? G of b is bigger than 0, which means that it's also bigger than 0 in some bubble around b. G of a is bigger than 0, or excuse me, less than 0, so that means it's less than 0 in some bubble around a. So let's see if we can use that to our advantage. Notice, oops, G is continuous as it's the sum of continuous functions. Also, we have, by subtracting y across this inequality that's given to us, we know this inequality, what would we have? We would have g of, well, here, I'll show the steps. F of a minus y is less than 0, which is less than f of b minus y. Again, that's simply subtracting y across this inequality. But this has another name, that's g of a. So I'll say i.e. g of a is less than 0, which is less than, this guy has another name, g of b. Okay. That's going to be helpful. And what I'm going to do now is let's come up with a set that we can use this completeness of R on. So what I'm going to say is let A be the set of x values in the closed interval a to b, such that I'm going to say g of t is less than 0 when for each t in the interval a to x. Okay. So I'm going to go back to my picture and kind of talk about what this set looks like. So this is the set of all elements a, or excuse me, all elements x, such that g of t remains negative from a up to x. All right? So let's look. So it looks like this value, x, that's going to be a member of my set A. A is a member of my set A. This member this x right here is a member of my set A because g of x is less than the x-axis or below the x-axis up to that x value A. And I can go further. It's less than the x-axis up to here and all the way up to, I don't know, some value. Okay, so we know A stretches along some finite distance, but let's look here. Notice A, or I'll say this, notice the lowercase a is a member of A since g of A is less than 0. So A is non-empty. Again, if I want to use this least upper bound property of the real numbers, I have to make sure that my set is non-empty and bounded above. So A is non-empty. But also, A is a subset of the set, the closed interval a to b, so B is an upper bound. So I have a non-empty set that's bounded above, Hence, by the completeness of R, A has a least upper bound. I'm going to call it C. Okay, now, there are three possibilities for f of C. Or excuse me, g of C. Either g of C is less than 0, g of C is bigger than 0, or g of C is equal to 0. This last one is going to be the one we're banking on, but what we have to do is show that this one's impossible and this one is impossible. So what we're going to do here in a second is suppose this is the case. But before I do that, I needed to show a very important tool for this proof. I did something similar in the boundedness proof. But what I'm going to show is that if we have our least upper bound here, C, and we grab any element that's less than C, then, or any number that's less than C, what we're going to show is that number must be a member of A, okay? So suppose this is going to be very similar to that other proof. L is less than C. Again, my goal is to show that L is a member of A, and that's always true. Then L is not an upper bound. Why is that true? That's definition of least upper bound C, okay? Go back to the definition. If you have any number that's less than a least upper bound, that means it's impossible for that to be an upper bound, because otherwise this wouldn't be a least upper bound. Okay. Hence, there is some member of A such that that member is bigger than L. Okay? That's what not being an upper bound means. That means A has to be bigger than it at some point. Hence, since K is a member of A, so K is a member of A, that means by definition, G of T is less than 0 for each T in the closed interval, A to K. But the closed interval A to L is a subset, proper subset of the closed interval A to K. Hence, G of T is less than 0 for each T in this closed interval. Oh, but what does that mean about L? So L is a member of A. So again, what we just showed, really important, is if I am a member, or if I'm a number less than the least upper bound C here, then I have to be a member of A, okay? That's crucial. Now here's where we go into our sort of contradiction argument. So we're going to suppose that G of C is less than 0 with this fact coming along with us. If we have any number less than C, then you are a member of A. That's going to be really important. Suppose G of C is less than 0, and we're going to find a problem with this. This is going to cause issues. Since G of C, oh, here, I really have to say something like this. By continuity at B, this is a subtlety. Since G is continuous at B, we know that G is, first of all, G of B is positive. That's something that we've supposed right here. G of B is positive. We know by that other theorem that G is positive around B. There is some delta 1 bigger than 0 such that g of t is positive whenever we grab the t from that delta bubble, b minus delta 1 to b. Hence, what we literally just found is a set of upper bounds of A. All of these are upper bounds of A because A is defined to be the closed intervals for which g is negative on, and this is an interval where g of t is, or where g is positive, which means those are all upper bounds, which means C as the least upper bound, let me say this again, C is, or all of these are upper bounds of A, and C is the least upper bound of A. So what that means is C is less than or equal to B minus delta 1, but that B minus delta 1 is strictly less than B. Okay, so that's important to say. In other words, C is definitely less than B. Okay, so that's like a weird, finicky thing I have to say because the next thing I want to say is this. So G is continuous at C. So, lots of so, thus, therefore, that's what a proof looks like. Thus, there is some delta 2 bigger than 0 such that, again, we are supposing that g of c is less than 0. And since g is continuous at C, that means there is a bubble around C, a delta bubble around C, such that g remains to be negative around or within that bubble. So that's what I'm going to say right now. There is some delta sub 2 bigger than 0 such that g of t is less than 0 whenever t is a member of that delta bubble. Okay, so what I'm going to do is grab a number on the left side of that bubble. Then, well, that number is less than C, and we just showed that if you are less than C, you are a member of A. But if you're a member of A, we know that g of t is less than 0 over I'll say for each, the defining property of being an A for each t in the closed interval a to x sub 1. All right, that's important. Now choose an x sub 2 on the other side of this delta bubble here. So I just grabbed a number on the left side. I'm going to grab one from the right side now. Then I think g of t is less than 0 for each t in the closed interval x sub 1 to x sub 2. Why? Because that closed interval is a proper subset of the larger interval within which I know g is negative. Okay, nice. Okay, so I know g is negative over this interval, this closed interval. But wait, I know g is also negative over this closed interval. That means that g is negative, is less than 0 for each t in their union. And you might see the issue. That is the same as the set from a to x sub 2. But wait a second. What that means is by the defining property of being a member of A is this. And therefore, x sub 2 is a member of A. But wait, that can't happen. x sub 2 is bigger than c. Not bigger than 0, bigger than c. So c failed as an upper bound. Okay, that is our contradiction. Hence, either, so what we just did is we eliminated one of these possibilities. We know that either, where is it? Here. There are three possibilities for g of c. Either g of c is less than 0, can't happen. That failed. That hypothetical went to dust. Two other possibilities are g of c is bigger than 0 or g of c is equal to 0. We're hoping this is the only possibility. So let's see if this one causes any problems. So hence either g of c is bigger than 0 or g of c is less than, or g of c is equal to 0. Suppose g of c is bigger than 0. G is still continuous. Still continuous at c. So there is, and it's also, so g is continuous at c and g is positive at c. At least we're supposing that. So there is some delta bubble we can make. A delta bubble such that g of t is positive over that, or g is positive over that delta bubble. So we got c minus delta sub 3 to c plus delta sub 3. And what I'm going to do is literally just grab any number on the left side of that delta bubble. I know g is positive in that entire interval, so I know g of 3 is positive. But wait a second, we also know that x sub 3 is less than c. But if I have any number less than c, I know that number is a member of A. But what does it mean to be a member of A? It means that g of t is less than 0 for each t in the closed interval from A to x sub 3, closed interval. So in particular, I know that g of x sub 3 is less than 0. Okay, so what I'm telling you is that g of x sub 3 is both positive and negative. That's an outrageous contradiction. Hence, g of c must be equal to 0. That's the only possibility left for g of c. But what does that mean? Therefore, f of c minus y is equal to 0. And that implies, therefore, f of c is equal to y. In other words, our function meets the intermediate value. That is the intermediate value theorem. And we did it, ladies and gents. Okay. So here we go. The whole point of this video was to do some patchwork over Stewart's calculus, Thomas's calculus. They wave their hand. They say, we're not going to prove these here, not even in the appendix, because it's too complicated. We have to talk about the completeness of the real numbers. We learned in the beginning of this video, we did a crash course in what it means for the real numbers to be complete and what makes the real numbers different than the rational numbers. And what we did, very powerful, is we fixed these famous textbooks and said, you know, with this new axiom of completeness, we can provide proofs to these big theorems, the big ones being The extreme value theorem, this is crucial for later in calculus when we prove something called the mean value theorem. The mean value theorem, which is the most important theorem in probably the most important theorem in differential calculus, rests on this fact. Now we don't need to rest on a shaky foundation. We have proven this fact, and that's very powerful. So stay tuned for when we use the extreme value theorem. It is under our belts. We have a proof. Due to the completeness of the real numbers that we give ourselves as an axiom, what makes the real numbers different than the rationals? With this new property of the real numbers, calculus is granted to us.